The key vocabulary we use in machine mechanics allows us to quantify how a machine changes force and motion, compare different designs, and calculate performance using clear formulas and experimental measurements. From an energy perspective, every real machine obeys the law of conservation of energy. However, not all the input energy becomes useful work, some is lost as heat, sound, or friction. Understanding each term in our vocabulary helps us track exactly where that energy goes. The three core metrics that form the backbone of machine analysis are mechanical advantage, velocity ratio, and efficiency. These are applied universally to levers, pulleys, screws, and inclined planes. Our study begins by defining effort, load, input and output work, and power. We then build up to mechanical advantage, velocity ratio, and efficiency before introducing the concept of an ideal machine and the empirical relationship known as the law of the machine. Effort, denoted by E, is the force applied by the user or by a motor to operate the machine. Load, denoted by L, is a resisting force that must be overcome or lifted. Both of these quantities are measured in newtons. The effort distance, represented as d sub E, is the distance moved by the point where the effort is applied. The load distance, represented as d sub L, is the distance moved by the load itself. These distances are measured in meters. The work input to a machine is given by the effort multiplied by the effort distance, while the work output is the load multiplied by the load distance. Both of these are measured in joules, and in every real machine, the work output is less than or equal to the work input due to unavoidable energy losses. From a power perspective, if the motion is steady, the input power is the effort multiplied by the speed at the effort point, while the output power is the load multiplied by the speed at the load point. Here, speed is simply the distance moved per unit time at each point. Mechanical advantage, spoken as MA, is simply how much the machine multiplies your force. Definition in words: MA equals load over effort. Verbalize it as MA equals L by E. If MA is greater than 1, your machine reduces the effort needed to handle the same load. If MA is less than 1, you're trading force for speed or distance, useful in sports equipment or human limbs. For example, if E equals 50 newtons and L equals 200 newtons, then MA equals 200 by 50 equals 4. In an ideal lever, MA would equal the arm-length ratio, but in real levers, pivot friction and bending reduce it, so the measured MA is a little smaller than the tidy geometry predicts. The velocity ratio, or VR, is defined as the distance moved by the effort point divided by the distance moved by the load. It is a dimensionless quantity that depends purely on the geometry or kinematics of the machine, and in the ideal case it is independent of friction. In common examples, the ideal velocity ratio for a lever is the length of the effort arm divided by the length of the load arm. For an inclined plane, it is the length of the slope divided by its vertical height. In a block and tackle system, the velocity ratio is simply the number of strands supporting the load. A large velocity ratio means the effort point moves a much greater distance than the load, which is useful for lifting heavy loads with a relatively small applied force. When comparing velocity ratio to mechanical advantage, an ideal machine has its mechanical advantage equal to its velocity ratio. In a real machine, the mechanical advantage is always less than the velocity ratio because of frictional and other energy losses. Efficiency, denoted by the Greek letter eta, is defined as the work output divided by the work input multiplied by 100%. It can also be expressed as the mechanical advantage divided by the velocity ratio multiplied by 100%. In essence, efficiency measures how closely the actual performance of a machine matches its ideal geometric advantage. For real machines, efficiency always lies between 0% and 100%, with 100% efficiency being possible only in an ideal, frictionless machine. Energy losses that reduce efficiency can come from many sources, including friction at pivots, threads and axles, bending of ropes, deformation of parts, and even air resistance. Good design aims to minimize these loss channels. For example, if a machine has a mechanical advantage of 4 and a velocity ratio of 5, then its efficiency is 4 divided by 5 multiplied by 100%, which equals 80%. The remaining 20% represents energy lost to these various frictional and deformation effects. In an ideal machine, the work output is exactly equal to the work input, meaning there are no energy losses. Under these conditions, efficiency is 100% and the mechanical advantage is equal to the velocity ratio. While this serves as a reference benchmark, it is never perfectly achieved in practice. The principle of a machine states that a real machine can never produce more energy than it receives. The output work can never be greater than the input work, and any difference between the two is due to unavoidable energy losses. The design goal in engineering is to make a machine's behavior as close to ideal as possible by reducing friction and optimizing geometry so that the mechanical advantage comes as close as possible to the velocity ratio. In practical terms, even if a machine has a high mechanical advantage, a low efficiency means much of the input effort is wasted. This is why both mechanical advantage and efficiency are important when selecting or designing a machine. Here's the practical way we characterize any real machine: measure the effort needed at steady speed for various loads, then plot E on the vertical axis against L on the horizontal axis. Empirically, the points line up nearly straight. We write E equals mL plus C. Speak it as E equals m into L plus C. The slope m tells how fast the effort rises with load. In a low friction system, m is close to 1 by VR. The intercept C is the effort you need to overcome friction even when the load is tiny: bearings, threads, seals. From any point on the line, compute ma equals L by E and then eta equals ma over VR times 100%. As you can see on the graph, reading off slope m and intercept C makes prediction easy. Let us consider a block and tackle system with 4 supporting strands, giving it an ideal velocity ratio of 4. The system is used to lift a load of 800 newtons at a steady speed, requiring a measured effort of 230 newtons. When the load is close to zero, the required effort is 30 newtons. We are tasked with finding the mechanical advantage, the efficiency, and the constants for the law of the machine. The mechanical advantage is the load divided by the effort, which is 800 divided by 230, giving approximately 3.48. The efficiency is the mechanical advantage divided by the velocity ratio multiplied by 100%. Substituting the values, we get 3.48 divided by 4 multiplied by 100, which equals about 87%. For the law of the machine, we use the equation E equals mL plus C, where C is the constant effort needed to overcome friction at no load. Here, C is 30 newtons. Substituting E equals 230 newtons at a load of 800 newtons, we find m equals 230 minus 30 divided by 800. This gives 200 divided by 800 or 0.25. Therefore, the equation for the machine is E equals 0.25 L plus 30. Interpreting the results, we see that the efficiency is high because friction losses are modest. The constancy value of 30 newtons represents the baseline effort lost to system friction, even when lifting very small loads. Let's quickly revise what we've learned about the technical vocabulary of machines. Effort and load are the forces dE and dL are the paths they travel, and those give us work in and work out. Mechanical advantage L by E tells the force multiplication. Velocity ratio dE by dL captures the ideal geometry, and efficiency MA over VR times 100% connects real to ideal. The dream case has MA equals VR, but real devices always lose some energy, well modeled by E equals ML plus C. I hope this clarifies how we measure a machine, not just describe it. With these terms, you can read any lever, pulley set, ramp, wheel and axle, or screw like a pro. See you in the next session, where we'll put this language to work on real mechanisms.